For the last part of chapter 13, we've been talking about equilibrium, these reversible reactions where the forward reaction is possible and the backward reaction is possible. We could have two product molecules collide with enough energy and reform the reactant molecules. So we have equilibrium. We imagine a system already at equilibrium, and I'm going to show you some different reactions that are equilibrium reactions. And then we have one more concept, and it's going to be that of what if we have a system at equilibrium and there's some disturbance to that equilibrium or stress, the equilibrium position can change a little bit. So we have this principle called Le Chatelier's principle. And once you get the hang of it, it's not too bad, but it's a little bit odd to start out with. So Le Chatelier's principle says that if an equilibrium system is stressed, the system will experience a shift in response to the stress that will reestablish equilibrium. I'm going to write that out real quick. So if an equilibrium system is stressed, if an equilibrium system is stressed, and we'll talk about what the stresses can be, the system will experience a shift, that reaction, the system will experience a shift in response to the stress that reestablishes equilibrium. So if somehow we kind of disturb a system at equilibrium, right, it's found this balance. The forward and reverse reaction rates are equal. It's found a balance on its own. If we do something to it, that equilibrium position can shift for a minute, either, not literally a minute, but for a little bit, either the forward reaction will go faster or the reverse will go faster until we reestablish equilibrium. And we're going to talk about what those stresses can be. There's four of them. Okay, so the first stress that we will consider is what happens if we change the concentration of one of the substances that's in that reaction. Could be a product or could be a reactant. What if we change the concentration? So I'm going to write a reaction out, and we're going to consider two scenarios. One is where we add more of something, and one is where we remove it. So we're changing concentration. We can either increase concentration or decrease it. So the effect of a change in concentration, I'm going to look first at what if we add more product. I'll put reactant first just because it's add more reactant or product. And we'll look generally at how it responds to adding more of something, reactant or product. Then, I'm going to separate it a little bit. Then we'll look at remove reactant or product. How does the system respond, reactant or product? So there's two parts of this that we're going to look at. And I'm going to put a reaction up. We're going to do a reaction of H2 gas. I'll leave a little space here. H2 gas plus I2 gas is in equilibrium with 2H gas. Okay. So we're looking at this reaction, and in order to consider Le Chatelier's principle, we look at this system already at equilibrium. It's reached that point where the forward reaction is the same rate as the reverse reaction. Now we add more of something, and it could be a product or it could be a reactant. I'm going to say, what if we add, and I'm going to even say, so the stress is going to be adding, increasing. I'm going to put an up arrow for increasing. We're going to add H2 gas to the reaction. Okay. Add H2. Add H2. Okay. That's going to be the stress. That's going to cause now something to happen. And according to Le Chatelier's principle, what it says is once we stress it, it's going to shift to reestablish equilibrium. So if we add more of something, what might the reaction do to reestablish equilibrium? And the way I always think of it when I think of Le Chatelier's principle is whatever the stress is, the reaction works to undo what we did to it. So if I add more H2, okay, I'm adding H2 here, the reaction is going to shift to kind of undo that. And when I say the word shift, what that's going to mean is either the forward reaction or the reverse reaction becomes, so shift, either the forward reaction or the reverse reaction becomes more dominant for a little bit. Okay. So if I add something, the shift is going to be to use it up. We want to, if we have extra H2, it wants to use the H2. And in this case, the only way to use the H2 is to react to make the product. If I add more of a reactant, it's going to make the forward reaction dominate for a little bit to use up that reactant that I added. So the shift is going to be a reaction in the forward direction. That's why I have this arrow here. The forward reaction is going to be more dominant. And then the effect of that, so we're looking at what does that mean for everything if we're just looking at the forward reaction being more dominant. The effect that we would observe is for the forward reaction, this is what I'm deciding this by the way the reaction is going to go. If the forward reaction is occurring, right, then that means we're using up H2, so we're actually going to see a decrease in the amount of H2 after we add it, right? We're going to use some of that up. We'll also see a decrease in the I2 because the H2 has to react with iodine in order to make the product. And then the result of the forward reaction is we see an increase in the product formation. So if we add H2, we end up observing I2 gets used up. Some of the H2 that we've added gets used up, maybe even more than what we added. And then the amount of I2, or HI, increases. Okay. So if I add more reactant, I see actually we end up getting an increase in the amount of product. Okay, the equilibrium shifts. If we look at adding more product, right, maybe I increase this up here instead, we would end up seeing a shift backward to use that up, and we would end up seeing this increase and the H2 increase. Okay. So looking at what you add, you're going to see a shift away from what you added and an increase in whatever is on the other side of the arrow, and then a decrease of whatever's on the same side of the arrow. Okay. So that's if we're adding more of something. If we are removing something from the system, we're going to look at the same reaction. If we're removing something, let's do H2 gas plus I2 gas makes 2, is in equilibrium with 2HI gas. If we're removing something from the system, maybe now instead somehow I let H2 out of the reaction mixture. Okay. Sometimes you can remove something by putting something there that the hydrogen can, a little competition that it can react with as well, like put in another substance that iodine won't react with, but hydrogen could. And it'll use up some of the hydrogen that's there. If we decrease or remove H2, okay, then we see a response to make more H2. If I take something out of the system, the response, according to Le Chatelier's principle, it's going to undo whatever stress that I imposed. If I take something out, it's going to work to make more of what I took out. So because the H2 is a reactant, it's going to work to make more, and that's going to mean the reverse reaction becomes dominant to make more H2. We're just looking at which way, which direction helps us undo whatever stress we imposed. And so then for looking at the effect of this stress, usually we're looking at the effect in terms of the concentration of the reactants and products. Now I look at, well, if the backward reaction is dominant, then that means I'm using up HI. The HI concentration goes down because I'm using it up to make more I2 and to make more H2. Okay. The reaction will respond to make more H2, more I2, and we'll see less HI. Okay. So I'm using arrows to show increase and decrease in concentration, but also to show which reaction, the forward or reverse, is going to dominate. So if you remove something, generally, if we remove something from the system, we remove it, the reaction is going to work to make more of it. So if I removed HI instead, right, maybe I let the product out, the reaction would work to make more of that. And I would see an increase in HI, a decrease here, and a decrease for H2 because we're working to make more HI. Okay. So it's a little bit weird when we're looking at what's the stress, what's the shift, which direction is the reaction going to go, forward or reverse, and what does that do ultimately to the concentrations of the reactants and products. But once you get the hang of it, it's not too bad. Okay. For some gas systems, so I think we looked at a system with like NO2 and N2O4. I'm going to look at that one. So for some gas systems, pressure is a change. Like what if we compress the gas, compress the gas mixture? So let's look at, I'm going to put a reaction up and then we'll talk about it. So the effective change in pressure, I'm going to put up, what if we look at 2NO2 gas in equilibrium with N2O4. The key with looking at how pressure or a change in pressure can affect the reaction is looking at, because pressure is determined by the gas molecules hitting the walls of the container. Okay, gas molecules hit the walls of the container. Container walls. So if we compress a gas or compress the reaction, right, we shrink the volume, we're going to see an increase in pressure. This is what we talked about back with gases. We see an increase in the pressure because there's more collisions with the walls of the container. In an equilibrium reaction, the reaction is going to work to lessen the pressure. What if the system is compressed by decreasing volume of the container? Okay. It's going to work to lessen the pressure. So let's imagine we even okay, I'll say the stress is increasing pressure, okay, by shrinking the container. Okay, maybe there's a piston, we can push it down further into the container. The shift is going to be whichever direction will cause the pressure to increase, to be relieved. Right? We want to see a decrease in pressure. Sorry if I said increase, I might have gotten that confused. The shift is going to be whatever direction allows for a decrease in pressure. And this is where we get to really kind of look at what the answer is for which direction we'll see a shift. We see a decrease in pressure with fewer moles of gas. Okay. We want to form fewer moles of gas. Less moles of gas is going to give less pressure. So what we go back and look at is up here, how many moles are in the reactant side and how many moles are in the product side. And what we do is look at the coefficients to tell us that. Okay. So generally, I'd say we have 2 moles of gas because of the coefficient 2 for NO2. 2 moles of gas on the reactant side and 1 mole of gas on the product side. Okay. So if we increase the pressure of this reaction here, if I increase the pressure on this, we want, the reaction wants to decrease the pressure, wants to relieve the pressure a little bit. And so it's going to shift to whatever side gives fewer moles. Whatever side has less moles shown in it by looking at the coefficients. So here, the effect, based on just this reaction, it can be different for different reactions, but the effect here is that we would see a decrease in NO2 and an increase in N2O4. The shift would be, I'm going to write it up here, the shift would be going in the forward direction because that is the direction that makes fewer moles overall of gas. So if we increase the pressure, it's going to shift in the forward direction in this reaction because that's the side with fewer moles of gas. So it's an increase in N2O4 and a decrease in NO2. Okay. So when it's asking about pressure, consider the coefficients, or maybe there's multiple of something, we have to consider all of that as well. And then we decide, do we expect the forward reaction to go or the reverse reaction to go based on which side has more or less moles of gas. In this case, maybe the stress, if we looked at a different scenario where the stress was decreasing pressure, maybe we expanded the system, right? So what if for a minute we look at decreasing impermanently? I'm going to just do this laser thing. What if we decrease it? The shift is going to be to increase the pressure, right? It wants to maintain that equilibrium. And so it would, to work to increase it, we would see a shift toward more moles of gas. So we would see a reverse reaction dominate for a little while, and we would see an increase in NO2 and a decrease in N2O4. Okay, that's if we had a different stress. The opposite was happening. Okay. Then the reverse would be true. Okay, so if you're looking at pressure, it's often a gas system, or some gas is present somewhere, and it has to do with the amount of gas that's present on the reactant side and the product side. And that's the coefficients. Okay. All right, so we're most of the way there. So we've talked about concentration and we've talked about pressure. We've got two more things to consider. Temperature is the third kind of stress of the four that we're looking at. Change in temperature, maybe we heat a system or we cool a system down. And really, how temperature affects a reaction depends on the heat of the reaction. So for a change in temperature, we have to consider the heat of reaction. So you would have to know somehow, consider the heat of reaction, and there's going to be two options. The first is, and it's mainly just the sign of it. Consider the sign of the heat of reaction. Is delta H positive or is it negative? For a positive delta H, a positive heat of reaction, this means the reaction is endothermic. Heat is required for the reaction to proceed. If you're not given delta H in a problem, there will be some way for you to know if it's endothermic or exothermic. Is heat required or is heat produced in the reaction? So for a positive delta H, we'll even look at the reaction that we just did, where we have, it's just going to be backwards, N2O4 gas in equilibrium with 2NO2, sorry, that's a bad arrow, 2NO2 gas. For this, the heat of reaction, the amount of heat required is positive 57.20 kilojoules. The amount of it, the number doesn't matter as much as the sign. This is going to be an endothermic reaction. You may just be given something that says this is endothermic. What do you expect the effect to be of changing temperature? So the reason we need to consider whether it's endothermic or exothermic is that if it's an endothermic reaction where heat is absorbed, heat is required for the reaction to go, we can imagine heat. If heat is required for the forward reaction to go, we can imagine heat as a reactant. Heat may be considered as a reactant. And I literally mean heat. So what I can do with this reaction is instead I can add on to the reactant side the word heat, if it's endothermic, that means heat goes in as a reactant. And now I can consider changes in temperature as changes in concentration, a little bit, right? It's going to be a little bit like that. So if the stress is, if the stress is increasing temperature, I'm imagining that as an increase in heat, right there, increase in heat, increase in this reactant amount, right, reactant concentration, then I can consider it the way we considered other concentrations of reactants. And so then the shift is to use up that heat. And if heat is required for the forward reaction to go, then if we add more heat, we're going to see more of that forward reaction. Okay. This is one way that you can make more product. If you have an endothermic reaction and we heat it, that's going to cause the forward reaction. And so we'll end up seeing ultimately the effect, right? The effect is a decrease in the reactants because the forward reaction is the one dominating. And we see an increase in the amount of NO2 that's produced. So if we heat an endothermic reaction, it's like adding more reactant and we make the forward reaction go. So here we're consider heating or cooling like increasing or decreasing the heat concentration. In quotes, because it's good. Okay, so heat is either a reactant or product, and we're adding heat is going to be like increasing it or cooling something down. Maybe we put it in an ice bath. Cooling it down would be like decreasing the amount of heat in the reaction. Okay, so we're going to look at temperature just a little bit more. So if maybe imagine like we still have the same reaction, maybe we decrease temperature instead. What if we were to cool it down, right? Maybe, I don't know how we cool gases down. Maybe we turn the temperature down or we put it in some cooler, right? We cool it down, we decrease the amount of heat. The reaction, we imagine this is like concentration of something. So if I remove something from the system, the effect is going to be to produce more of it. So if I decrease the heat here, I'm going to see a shift backward, okay, to make more of it. And if we have the reverse reaction dominating, that means we decrease the product and we see an increase in the amount of reactant present. So this is kind of the first picture. If we have an endothermic reaction, the other option is if we have an exothermic reaction. So if we have a negative delta H, this is exothermic. And this means that heat is produced in the reaction. Heat's given off. And this means that heat may be considered as a product. Heat may be considered, as a product in the reaction. Heat is produced. Heat's given off, maybe as light, or it's heat you can feel, right? You mix two things together and the test tube gets hot. That would be exothermic. And so what I would look at is, let's even reverse this. If we reverse the reaction, so 2NO2 gas makes N2O4. The delta H here, the heat of reaction, the amount of heat involved is the 57.20, but if I reverse the reaction, we get the negative amount of it. So now I have a negative delta H, and that's going to mean exothermic. That's going to mean heat is lost in this reaction. Exothermic. So that means if it's lost in the reaction, that means it's produced. We can imagine it being a product, and I can add it in on the product side like that. Add it in on the product side, and then we can imagine it being a product. And what happens if we heat or cool this reaction? So I'm going to imagine we cool it. Let's say the stress is decreasing temperature. Decreasing T. Decreasing the temperature. We lower the temperature. The shift is going to be to, if we lower the temperature, it's going to be to make more of that energy, to make more heat. And so if we're sucking heat out of the reaction, it's going to work to undo that. So we're going to see a shift toward whatever we're removing, a shift to make more of whatever we're removing. And then the effect of that shift, of this forward reaction, is to see an increase in the product and a decrease, oops, it's kind of in the wrong, and a decrease in the reactant. Okay. So when I'm looking at the effect, I'm looking at this answer. Is it the forward reaction or the backward reaction? If it's the forward reaction, then that always causes a decrease in reactants and an increase in the amount of products. Okay. And so the difference here between these two situations is you have an endothermic reaction. That means heat is a reactant. You have an exothermic reaction, meaning the negative number here. That's going to mean you put heat. Just the word, doesn't matter the amount at this point. Okay. It's just where do I consider heat over here, or do I consider it over here of the arrows? And if it's exothermic, then we just add the word in, and then when we're changing temperature, decreasing temperature, then we can look at heat and say, okay, it's going down, and then go from there. Okay. So that's most of it. The last thing we kind of want to address is, we talked about catalysts earlier in chapter 13. And we said that catalysts, their function is to increase the rate of reaction, right? So catalysts, I'm going to make this bigger. Catalysts increase reaction rate. So they increase reaction rate. They make the reaction go faster. But they don't have anything to do with equilibrium. So chapter 12 was reaction kinetics, reaction rates. Catalysts can get you faster to the end point, but it doesn't change where that end point is. Okay. So if it's an equilibrium reaction with a catalyst, the catalyst is there and it got you to equilibrium faster, but adding a catalyst to a reaction at equilibrium does not affect anything. So it makes the reaction go faster to its end point, but they don't cause a shift in equilibrium. They don't cause a shift in equilibrium. Okay. So if you're looking at a question where it says, here's a reaction, right? Blah, blah, blah goes to blah, blah, blah. And it says, what do you expect the effect to be of adding a catalyst? There is no effect. Catalysts have no effect. On, in terms of Le Chatelier's principle, on equilibrium. They do cause a change at the reaction rate. So chapter 12 questions, they do matter. For chapter 13 questions, where we're talking about equilibrium, they don't have an effect. No effect on equilibrium, or no effect in terms of Le Chatelier's principle. Okay. So that's the last part. Catalysts have no effect on equilibrium position. There's no shift in the equilibrium according to this section. Okay.